The word nuclear usually conjures images of massive reactors, heavy lead shielding, and years of dangerous waste. But a new class of power cells turns that same radioactive material into the ultimate energy source for drones without any moving parts, heat generation, or danger to the operator. This technology bypasses the physical wall that lithium-ion batteries have hit. As you add more range, you add weight, which requires even more energy to lift. We are not building mini-reactors on aircraft wings. Instead, we harvest the raw decay of nuclear waste directly into electricity using a sliver of material derived from industrial byproducts. This shift from generating power through heat to harvesting decay particles solves the specific bottleneck where longer flight time used to mean impossible payload penalties. For decades, the promise of long-endurance flight was trapped in an infinite loop of physics that chemical batteries could not escape. When you want a drone to fly for hours instead of minutes, you must carry more fuel or larger batteries. But every gram added to lift capacity reduces the total energy available for propulsion. The heavier the battery, the harder it is to stay airborne. This creates a hard ceiling on how long any chemical-powered device can remain in the sky before returning to base to swap out its power source. Engineers have pushed lithium-ion chemistry as far as it will go, but they are now hitting a fundamental limit where adding more energy simply adds too much mass to overcome gravity efficiently. The solution lies not in better chemicals, but in a different form of physics entirely: betavoltaics. These devices do not generate power through heat or combustion like traditional nuclear fission reactors. Instead, they operate on the principle of direct charge extraction from radioactive decay. They harvest low-energy beta particles, which are essentially electrons emitted when unstable isotopes like tritium or nickel-63 break down over time. By converting these particles directly into electrical current via semiconductor junctions, we eliminate the need for complex thermal conversion machinery and heavy radiation shielding that would make flight impossible. This approach represents a fundamental shift in how we think about energy harvesting. We are not creating new energy from nothing. We are catching a slow, constant drip of power released by nature itself. Imagine a leaky bucket where water constantly drips out to fill a cup below. The chemical battery is like trying to carry the whole bucket up a mountain every time you need a drink, while betavoltaics provide a steady stream from a reservoir that never empties in any practical time frame. This allows electronic devices to run for decades without needing a recharge or replacement, turning what was once considered waste into a stable power source. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Historically, the application of this technology was limited by a significant materials science problem: radiation damage. The very particles generating the electricity would eventually bombard and destroy the silicon semiconductors used to harvest them. For years, betavoltaics were confined to niche applications like deep space probes or medical implants, where size constraints justified complex engineering solutions. However, recent breakthroughs have introduced a new class of materials that changes everything: synthetic diamond semiconductors. Diamond's crystal lattice is incredibly robust against radiation damage compared to standard silicon. While the high-energy particles might shatter ordinary semiconductor material like glass under stress, diamond acts as a shield against itself. This allows the device to maintain its efficiency for decades, even while being bombarded by decay particles that would destroy conventional electronics. This breakthrough in materials science solves the lifespan bottleneck and opens the door for betavoltaics to move from specialized medical devices into broader aerospace applications where reliability is paramount. The supply chain reality of this technology adds another layer of intrigue. These isotopes are not mined from exotic new sources or created through expensive synthesis processes alone. They are often extracted directly from nuclear waste streams. Tritium, for example, is a byproduct of heavy water reactors that can be harvested at scale. This creates a circular economy where what was once considered hazardous material becomes the fuel source for high-value applications like aerospace and robotics. The density of this energy means a device powered by roughly 41 grams of active isotopic material can outlast lithium-ion batteries in terms of total energy output over time, even if its instantaneous power is lower than a standard cell. To understand why this matters for drones specifically, we must look at the math of the third dimension. As noted by researchers and aerospace engineers, lifting objects into the air requires a much higher power-to-weight ratio than ground vehicles. Every gram of battery added to a drone reduces its payload capacity or flight time exponentially because gravity is always pulling down while you pay for lift with energy. Because betavoltaics offer an energy density that does not degrade with weight in the same way chemical reactions do, they solve the specific bottleneck where longer range used to kill the payload. This technology was first successfully deployed commercially decades ago when it powered cardiac pacemakers implanted into patients starting around 1970. Over 5 years following those initial surgeries, more than 1,400 additional people received nuclear batteries for their devices, proving that this power source is safe and capable of lasting a human lifetime without recharging. The same principles now apply to drones intended for surveillance, environmental monitoring, or infrastructure inspection where returning to base every 40 minutes becomes a logistical nightmare. A drone equipped with a betavoltaic cell does not just fly longer, it becomes an autonomous sensor node that can stay aloft or on-site for years, effectively removing the need for battery swaps and charging infrastructure. The biggest barrier has always been fear, but these batteries do not emit dangerous gamma rays requiring lead shielding. They only release low-energy beta particles that are stopped by a thin layer of plastic or even air. A drone with this power source poses no radiation risk to the operator and can be handled safely in environments where traditional nuclear tech is forbidden. This isn't just an incremental improvement, it's a shift from chemical storage which leaks and degrades over time to nuclear harvesting which remains stable for decades. For applications like deep-sea monitoring or remote infrastructure inspection where recharging is often impossible, betavoltaics offer a path to truly maintenance-free operation. The physics are clear. We trade the high peak power of lithium-ion for an energy density that allows us to ignore weight penalties entirely when it comes to long-duration missions. The future of autonomous flight relies on solving this specific engineering constraint where chemistry fails and nuclear decay succeeds. By turning waste into fuel, we create a sustainable loop that powers the next generation of technology without adding mass or requiring dangerous infrastructure. The era of constant recharging is ending for high-value applications because the physics of energy density has finally been unlocked through materials science innovation. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.